We are going to reproduce Newton's thought experiment, which allowed him to prove Kepler's second law. To conduct his thought experiment, Newton relied on his first two laws of motion, namely that a body will continue to move with constant velocity as long as no forces are applied to it. This, of course, is his law of inertia. And his second law, force equals mass times acceleration, or in other words, mass times the change in velocity divided by the change in time. Other than that, he simply relied on good old Euclid's geometry, the concept of vector addition, and his potent imagination. Okay, so let's imagine planet Q traveling through our solar system. For our thought experiment, gravity has been turned off for the time being. At noon, planet Q finds itself at position A. Now let's imagine planet Q is traveling with velocity v, such that after 1 hour, it arrives at position B. Note that I am going to scale all velocity vectors so that the length in the diagram matches that of the distance traveled during an interval of 1 hour. This will allow us to visually equate velocity vectors with their corresponding displacement vectors as we think about the issue at hand. In accordance with Newton's law of inertia, there being no external forces at play, Q now continues at constant velocity and after 1 more hour arrives at position C. Because Q's velocity is constant, the distance traveled over 1 hour time interval is a constant, so that the distance from A to B is the same as the distance from B to C. We can construct two triangles as shown here. Let's call them Virgo and Taurus. Question: is the area of Virgo equal to the area of Taurus? Well, let's find out. Notice first of all that they share one side, now shown in magenta, which we hereby establish as the base of both Virgo and Taurus. Here I have drawn the altitudes of Virgo and Taurus, shown with the green dotted lines. We have thereby formed two new triangles, smaller than Taurus and Virgo, which I've labeled number 1 and number 2, and we are going to proceed by showing that triangles 1 and 2 are congruent. Remember that the distances from A to B and from B to C are equal. The angles shown here in orange are equal because they are opposite angles of intersecting lines. Furthermore, each triangle contains a right angle formed by its altitude and its base. Triangles 1 and 2 are therefore congruent based on the side angle rule. So we conclude that their altitudes must be equal. Remember that these altitudes are also the altitudes of Virgo and Taurus. Moreover, since these triangles share a common base, and their altitudes are equal, their areas must be equal. So, planet Q, with gravity turned off, is sweeping out equal areas in equal times. Now let's go back in time to the point when Q is at position B, and let's turn on gravity for a brief instant. I have shown that brief instant of force from the sun by drawing in a red vector, shown here. Or, as Newton himself put it, let it be attracted towards the center S by one impulse or impression of force. An impulse has a formal definition in physics. It is a vector, and it is closely related to the force vector. It is defined as F times delta t. Here, Newton specified that delta t was to be considered very small, and so I have used the lowercase Greek letter to represent delta. An impulse produces a change in momentum, delta p. Now, momentum equals mass times velocity. Assuming mass to be constant, we can say that the change in momentum caused by the impulse produces a proportional change in velocity. For our purposes, we don't need to know the magnitude of the gravitational force, and we don't need to know the magnitude of delta V. We simply ascribe an arbitrary magnitude to it. All that matters is that it points directly at the sun. Recall that all velocity vectors are scaled so that their length in the diagrams matches that of the displacement of q that would occur over 1 hour's time. Therefore, as planet Q travels on from point B, its path is now influenced by two velocity vectors, the original velocity v and the new velocity delta v, so that we must add these two vectors to produce a resultant vector which we will call v prime, and we will use v prime to plot the course of Q over the next 1 hour. To perform this addition, we make an exact copy of delta V and place its tail at point C. The resultant, V prime, brings Q to point C prime at exactly 2 p.m. This forms a third triangle, which we will call Pisces. Let's compare its area with that of Taurus. I have drawn in their altitudes here. Notice that delta V, as shown here connecting C with C prime, is parallel to the common base of the two triangles. Therefore, the altitudes are equal. And because they share the same base, the areas of Taurus and Pisces are equal. Remember that the area of Virgo was equal to the area of Taurus, so we have now shown that the areas of all three triangles must be equal. So, even though we turned gravity on for a brief instant and it deflected the path of Q at point B, the areas of Virgo and Pisces are equal. You can imagine carrying out this same series of logical steps, turning on gravity for brief instants of time, all the way around the orbit. In fact, this is exactly what Newton did, as shown here in a sketch from his notebooks. Now, if we can imagine turning gravity on for brief instants every 1 hour, we can also imagine turning it on more and more often until the intervals during which gravity is turned off become infinitesimally small. The areas of the triangles produced become smaller and smaller, but they are all still equal. The planet is sweeping out equal areas in equal intervals of time. In mathematical terms, we can say that delta A divided by delta T is constant. Using analytic geometry invented by Descartes around the time of Newton's birth, we can graph area as a function of time. As shown here, it is a line of constant slope, m. If we now denote the instantaneous rate of change of area as dA dt equal to the constant m, we have not only proven Kepler's law, we have most likely found one of the key fundamental ideas that led Newton to invent calculus.